Hey folks, this is Major Jones here to give you the last lesson on control hazards. We're going to look at one more technique, which basically all processors use at this point to help resolve control hazards, and that's a technique called branch prediction. We'll describe to you what that is, how it works, and then also, like before, we'll discuss sort of the effect of this technique on the actual performance of the pipeline. So let's get started. The last strategy we're going to look at, this one that we're going to look at today, is to predict. So some smart folks at one point said, hey, there's a lot of these branches where they have a history to them. If we took the branch last time, chances are pretty high we're going to take the branch again. You can imagine, a loop that executes 100 times in a row. Well, 99 times it's going to take the same branch, and it's only on the last one that maybe it doesn't. We sort of exit our loop, and so we can potentially improve our ability, we can reduce the penalties we pay from taking these branches if we can correctly predict whether it's taken or not. And so that involves some extra hardware here, which I want to show you. So number one. I'll tell you, we have what's called a branch target buffer. So this is a piece of hardware that goes in the fetch phase, and it's sort of activated whenever I pull out a branch instruction out of memory. So if I'm about to, if I'm fetching a branch instruction, then this buffer here sort of records, the last time that branch executed, whether it was taken or not. So here, a simple way to do this is if we store the address in memory of the actual branch instruction, right? We can use the address to uniquely identify which branch instruction we're talking about. And we'll keep things simple. We'll say, we're just going to store one bit sort of associated with that branch instruction. 0 means it was not taken the last time it showed up. A 1 means the branch was taken the last time it showed up. And so then what we'll do is we'll use this to figure out, okay, if this branch is being fetched and the last time it came up in the pipeline, it was not taken, well, then we'll sort of make the same prediction. We'll say, okay, well, it's probably not going to get taken again. And so the program counter will get just sort of incremented by 1. If that same branch instruction comes up, or a different one comes up, and the little table here says, it was taken last time. The last time this branch instruction was in our pipeline, we did execute that branch. Well, then we give the program counter what would be the result of that branch target in the hopes that, if it did it last time, it's going to do it again this time. And you can see kind of here that this is the little state diagram that sort of, captures that logic. If the branch was not taken, if the branch was not taken, then the next time we're going to predict it was not taken. And as long as the branch is continuously not taken, we're going to keep predicting that it wasn't taken. As soon as the branch is taken, we sort of update our prediction. We'll say, okay, we're going to change that bit from a 0 to a 1 to say the last time it executed, it was taken. As long as it is taken every time, then we just sort of stay with this prediction. And as soon as it's not taken, we move back to this initial state. So pretty simple. Branch prediction gets way more complex than this, but this is a very simple example to show you how this works, right? So we can kind of keep track of where the, whether the branch was taken or not taken last time to sort of try to make an educated guess. And so what that means is that as this branch works its way through the pipeline, eventually, it gets here to the execute phase. And when this branch actually executes, we need to confirm that our prediction was true. And if not, we got to update our program counter correctly. So, a new sort of little value that gets passed between our pipeline stages is our actual prediction. And the branch unit here is going to sort of take that prediction bit, compare it against whether or not the branch is being executed. So you can see, let's see, what do I want to show you? Okay, I want to show you up here. If the branch is in the execute phase and it does not match our prediction, that means it's either we're taking the branch and we thought we weren't taking it, or we're not taking the branch but we thought we were. In either case, I've got instructions here backed up in the pipeline which are not the right instructions. That means I got to sort of start over. So in that case, my branch unit's going to put some bubbles in here to sort of flush the pipeline, and we're going to use sort of the encoder from last time to say, okay, in that case, we got to restart. We got to send a new value to the program counter. So it's going to get this value here, which is coming from this multiplexer in the execute phase. The inputs to this multiplexer are the program counter, which was the value of the program counter when we retrieved the branch instruction. Or this input here is the offset calculated for this branch instruction, right? So effectively, this line is the program counter that I want to have if my branch was taken, right? Program counter plus offset. The actual value of the program counter plus 1, the one that points to the instruction right after the branch, is what I want to be my new program counter if the branch is not taken. So branch not taken, if that's 0, then I have to grab what is sort of like that old value for the program counter that points to the instruction immediately following the branch. And if the branch is true, that means, or if I am taking my branch, that means I got some instructions here which are incorrect because I predicted something else. And if I take my branch, then I want PC plus offset, the actual branch target here. And so based on the value of whether I take my branch, I send the correct value of into my program counter here, and flush the pipeline and sort of have to start over. However, if I get to this stage here, if my branch gets to this stage, and my prediction matches the branch, well, then this thing is not true. I've succeeded. My branch prediction did what it had to do, and I can just sort of move on, right? This branch I don't actually have to execute because I already fetched instructions assuming it was taken or not taken, and I ended up being correct. So after this, all I need to do is sort of continue with my encoder, figuring out which branch to take based on kind of like here, whether which branch instruction is in which stage moving backward. So I have my jump JSRR here in the read register phase, just like before. You'll notice I moved my JSR. It was coming out of the evaluate address stage. I moved it back here, and the reason is because if my branch target buffer predicts that the branch is taken, well, then I need to add my program counter to my offset anyways. I've got to add, I effectively have to do this addition all the way back here in the fetch phase. So one downside to this prediction solution is that I'm starting to add some complexity and some extra hardware to my computer that doesn't necessarily need to be there. And if I've got an adder back here, which is adding the program counter and the offset, well, why the hell am I going to wait all the way until this stage to evaluate my JSR? I might as well just do that in the fetch phase. So I'm I'm putting an adder all the way here in the fetch phase to do some PC plus offset. And if it's a JSR instruction, then I add that offset to the program counter and send it in here. And if it's a branch instruction and I'm predicting that it's taken, then I just add a slightly different offset and send that into the PC. And you can see that here, right? If there isn't, as long as there's a branch instruction, if there's no branch instruction in the execute phase, or if there is, but I predicted it correctly, then this first condition is not true. The next one I check is whether or not I have a jump or JSRR instruction in the read register stage. All right, if there is, then encoder gets 1, 0, and the PC gets that value. Lastly, I ask myself, is there a JSR instruction in the fetch phase, right? Which would mean I update my program counter. Or is there a branch instruction in the fetch phase and my prediction bit is saying that I think this branch will be taken? In those cases, then I give PC the value of whatever is in this adder, and those are control signal here. Clearly, that's going to select the correct offset for which instruction is in the fetch phase. And just like before, I've got this empty slot down here for my encoder 00, which is if none of these are true, then there are no branches I need to worry about. And so my program counter gets just program counter plus 1. All right. So now I can update down here my penalties, right? Last time, strategy number 2 was just sort of moving the execution of my JSR, jump, JSR instructions a little earlier. That got me some pretty good improvements. Now, when I include my prediction stuff, I can cut this down even more, right? JSR, which was previously there was a 2-cycle penalty because it wasn't evaluated to the evaluate address stage. Now I'm down to 0 because this is always taken, and I added some hardware in the fetch phase. So as soon as I see that JSR instruction, boom, the very next instruction to the program counter is the correct one, 0-cycle penalty, which is pretty cool. The branch instruction, it was previously always a 4-cycle penalty when that branch was taken, and always 0 cycles when it was not taken. Now I can get 0 or 4, right? And this depends in both cases basically on whether or not my prediction was correct. If my predictor is 100% correct, then my cycle penalties for my branches are always 0. But if a branch instruction comes up and my prediction is incorrect, then I have to pay that 4-cycle penalty to sort of flush the pipeline and refill with the correct instructions. So, this can be super powerful, this branch prediction, right? But like you saw down there, it really depends on how accurate it is. Thankfully, it's my understanding that modern branch predictors can achieve higher than, I think, 80% accuracy, which, definitely makes up for the potential cost in most cases, but it's something I need to account for. Jump and JSRR here are still a 1-cycle penalty, unfortunately, and that's just because in here at least I have to read from the registers, and so when they're being evaluated in this stage, I have at least one instruction in the fetch phase already that I have to dump when these are evaluated. So no improvements there, unfortunately, and they're still subject to stalls from read after write hazards. But getting to here where my cycle penalties are 110 and 0 or 4 is a whole heck of a lot better than where they were originally, all the way back when my very simple solution was just to stall, and I paid a 4-cycle penalty for every single branch I took. So those are some pretty significant savings. And again, it really matters because the more control hazards I have in my processor that I have to deal with, cycle penalties and no ops and things like that, the less performance I get out of my pipeline. So anyway, that's all I got. That's branch prediction. I'll see you next time.